Hi there and welcome to this video. Today we're gonna take a look at a simple truss example. Let's get started. So I have some notes here which I want to discuss shortly with you to understand the theory behind this. So I have a simple truss system consisting of two trusses which are connected to each other at node 2. And on node 1 we have a fixed constraint which constrains the only degree of freedom we have in the system, which is displacement in u. And u is right over here, positive into the right direction. And we have an external force, F3, which is acting on the system on node 3. And the question is, how are we going to calculate the displacements on node 1, 2, 3 for the system resulting from the external force? And this is an easy example to show how the finite element method works from a theory basis. So in the finite element method, we want to just take elements from which we know how they behave on the structural loads and assemble them back together to our complete complex system. So in this case, it's not that complex, it's just two trusses connected to each other, but the general method is the same. So we have an element, which is a truss, and the truss consists of two nodes, two possible forces, two possible displacements, which is denoted over here. And we want to take the sum of forces on node 1 and node 2 to see how the force acting because of the stress in the material is calculated. And for that reason we have here this equation which sums up the stress force, which is defined by the stress divided by the surface area, and stress again can be defined as the Young's module times the strain, and the strain is the elongation divided by reference length. So you put this all together, you get a equation between the forces acting on the system and the displacements of the nodes. So you have your stiffness term over here, which is denoted as K within the rest of these nodes. Alright, so we have node 1, we make this sum of forces equals 0 because the system is not moving. And on node 1 we have the force 1 and the force acting because of stress in the material. Note that the direction is then positive when the stress is a tension stress. So that's just definition, but you have to make this definition to be consistent in the system. Alright, so if you make your sum of forces and calculate that down there, you have your stiffness term right here and your displacements right here. And you can do that for node 2 also and get a similar equation. But note here that the stress force is acting on the opposite direction as in node 1. Putting those two equations into a matrix form results in an unbound matrix formulation. Unbound, I say that because it's just one element. It's not connected, it's not global, it's not our system, but it's a local unbound equation. So F unbound equals the K unbound times the U unbound. And back to the truss, we can differentiate between this unbound structure and the global structure. So the unbound structure would have two forces and two displacements for each beam, or each truss in this case. And on the other side, the global forces and the global displacements are just free, because we just have free global nodes. Setting up the stiffness matrix for the unbound structure is easy. It's just the two elements, and with this equation we can get to this. And I see that something is missing here. You have the displacements. Right over here. So yeah, that's the unbound structure, but we have to map this global. So into the global perspective, into the systems perspective. And for that reason, we first couple global and local displacements. So you can see the 4 displacements over here. They are corresponding to displacements in the global perspective, and you can express that with a Boolean matrix. So you denote 1 wherever the displacements are the same, and 0 where they are not. So U1 of element 1 is the same as U1 global, and U2 of element 1 is the same as U2 global, but also U1 from element 2. And this is the way you do that with the forces also. So you have the global forces, you have your Boolean matrix, you can use the same matrix, just transpose it over here and act on the global forces. This can be shown with the Whittle work, because Whittle work in both systems have to be equal, and so from that equation you can derive that this has to be transposed to be used in this, but that's not that important. Going farther down here, you can now state that your global forces, so this equation over here, you can say that your local forces are the stiffness matrix times the local displacements or unbound displacements. And the unbound displacements are the global displacements times this Boolean matrix over here. And so you get the relationship between the global forces acting on the system and the global displacements. And this stiffness matrix, which is the local stiffness matrix times the Boolean and the Boolean transpose, is now our stiffness matrix of the system. Multiplying that out results in this equation or this matrix. And this matrix is further intuitive because you have the both stiffness matrix which are just coupled together on the node 2. So in node 2 you have K1 plus K2. So makes sense. Yeah, and this results in your global equation. So your global forces equals the global stiffness matrix times the global deformations or global displacements. Now you have your boundary conditions. As stated above, we have just F3 acting here, and F1 is F1 globally is 0 because you have just no displacements at node 1, and F2 is also 0 because F1 of 1 and F2 of F2 of element 1 and F1 of element 2 are the same and acting in different directions, so they are summing up to 0. And the other boundary condition is that on node 1 we have no displacements at all. And this we implement like here. So F1 and F2 are 0. You have your U1, which is 0, and now setting F1 and F2 externally, not internally, you have to differentiate. So F1 and F2 externally is 0. So you're just putting a 0 here, and U1 is 0, and for that you just take the column 1 and the row 1, and all values go to 0 except the diagonal of 1, 1. So this remains 1, because then your first equation equals 0 equals 1 times U1, and that's just what the boundary condition is saying. And as F3 is giving, so you solve for the displacements, and you do that by inverting the matrix here and multiplying it with the forces matrix. Alright, that's about the theory. Now let's get this working and compose. So I have a little code. A little program coded here, and this can differentiate between user input and standard values. We go with the standard values for now. So we have a surface area of element 1, length of element 1, stiffness of element 1, and the same for element 2. What this calculation does is it calculates the stiffness terms, which are equal to the surface area times the stiffness divided by the length. And then you can put your system matrix for element 1 and 2. But now for simplification reasons, I just use the global stiffness matrix. I could use maybe for later reasons with the Boolean matrix and combine them together. But right now I just implemented the stiffness matrix globally. And here are the boundary conditions, which are setting the first column and row to 0 and the diagonal element to 1. And the force vector is equal to 0, 0, force. And here's the solving step of the equation, and this is just the leftover. And at the end you get a nice little message if it worked or not. So for this system I defined over here, we have this stiffness matrix and this displacements. Yeah, that's about it for this program. If you liked this video, please give a thumbs up, would be very happy about it. If you have questions or want to ask something, please leave a comment, it's no problem, I'm happy to answer those. And if you have further recommendations how to put this, what you want to see, is it a beam or maybe a 2D element calculation, just let me know.